Hello everyone, welcome back to another video. This is meant as a follow-up to the previous video, and I thought we'll have another look at a circular motion rough cone kind of question. Let's read it first of all. We have a hollow right circular cone, 4a base, 4a height. Okay, we have a particle mass m, horizontal circle, on the rough inner surface with angular speed omega. We even get given a coefficient of friction 1/4. We want to find the value of omega. I hope if you watched my previous video that right now you're thinking to yourself, this is almost identical as a question, because it is. And the examiners don't have that much flexibility with these sort of questions, so hopefully you can see the similarities already. Our approach is very much the same to this question as well. So I would always recommend you start by thinking about this triangle and some key lengths for us. So I'm going to sketch a similar triangle to this one, but I'm just going to draw half of the cone, because we only really care about half. This is supposed to be a right angled triangle, by the way. So this length here will be 4a. This is the height of our cone, and half of the diameter, our radius of our cone, would be 2a. Like in the previous question, we will consider theta from the vertical. So I'll label a theta in here. And with some Pythagoras, 4 squared plus 2 squared is 20. And root 20 will be 2 root 5a for this side. If you remember also what we did before, I think it's really helpful at this point to now consider a value for cosine theta and for sine theta, respectively. We know we're going to have to use those later on. So cosine theta is 4a over 2 root 5a. 4a over 2 root 5a. And we'll leave it irrational with a surd on the bottom. Should simplify to 2 over root 5. Let's do the same for sine theta. So opposite divided by hypotenuse should be 2a divided by 2 root 5a. So this should just simplify to 1 over root 5. I'm sorry if you're offended by leaving them with a surd on the bottom. Let's not worry too much. We've done this part. Next part is now considering some forces for ourselves. So forces on this diagram, let's change color. I can always mark in, this is our particle where it is here, can always mark in an mg pointing downwards for particle mass m. Same as we did before, we can mark perpendicular to the rough surface of the cone, a reaction force. And now here's the part, actually, let's go back and read the question really, really carefully. We want to find the greatest possible value of omega. And this is very, very similar to the one before. The greatest value of omega means that the frictional force is going to be pointing diagonally down along the surface of the cone, trying to hold our particle into the cone. If this wasn't acting, the particle would fly out of the cone. So we need to mark in our mu r acting down the surface of the cone like this, mu r. Yeah, this is the maximum angular speed. If it was a minimum, it would be acting upwards, trying to stop the particle falling down the cone. Yeah, you get the idea. Those are the only 3 forces we need to consider. But actually, before we proceed at this point, we should do one more bit of thinking. And this is adding in the radius here for our circular motion. So if you consider these, we had 4a height, 4a diameter. So that would be 2a for the radius. If we have 3a for the height, this should be 1.5a or 3 over 2a for the radius. I'm going to put 1.5a. fraction also would be fine. Final step on our diagram then, we're almost ready to leave it, is marking in our thetas. Yeah, really, really important to do this step carefully. Theta from the downwards vertical will be the same as this theta here. These are alternate angles. And like we did before, we can add in a vertical to help ourselves. This angle here must also be theta because they're vertically opposite. And because two thetas will never be adjacent on a diagram like this one here has to be a theta. Yeah, those are all the ones that we need to resolve vertically and horizontally. So having said that, let's move on to that step. Resolving vertically is a good idea here first. Let's go down here, making our thinking very, very clear to ourselves. We are going to be resolving forces vertically. Let's consider the forces acting vertically then. We have got an r sine theta acting up. So r sine theta. That's the only force acting up, and we'll think about our two forces acting down. We definitely have an mg, and the other force acting downwards is a mu r cosine theta. You have to crush that angle to go down. So plus mu r cosine theta. This is good for us because we know the value of sine theta, we know the value of mu. Let's put all of those in and see if we can find r somehow. So r brackets, sine theta was up here, it was 1 over root 5. 1 over root 5 equals mg plus mu was a quarter, so 1 over 4. Cosine theta, I'm doing this a bit out of order, put r here. Cosine theta was 2 over root 5, yep, 2 over root 5. Let's sort out our fractions for ourselves then. So r 1 over root 5 equals mg plus, this will simplify to 1 over 2 root 5 r. And moving both our r's over onto the same side, we've got 1 over root 5, take away 1 over 2 root 5. This just leaves you with a 1 over 2 root 5. So 1 over 2 root 5 r, make that an r, equals mg. R equals 2 root 5 mg. Exact same as last time. From resolving vertically, we've come up with a nice expression for r in terms of mg. Think back to last question. The second step will now also be the same. We're going to resolve horizontally, so this way, pointing from right to left, because this is the direction that we see our centripetal force acting in. So let's consider the forces acting in radially. We've got an r cosine theta. Zoom in, r cosine theta. And this time it's a bit different to the vertical one. You also have the horizontal component of mu r acting radially inwards. It's a mu r sine theta. So r cos theta plus mu r sine theta equals, and there's nothing balancing this out, is there? This is because it's centripetal force. So what we're saying here is these two forces combined give us an m omega squared r. That's our governing equation for centripetal force, circular motion. Well, we can do a bit with this because now we have a value for r. So reminding ourselves, our value for r was 2 root 5 mg. So here I'm going to replace this with a 2 root 5 mg. And also reminding myself, cosine theta is 2 over root 5, sine theta 1 over root 5. So 2 root 5 mg, 2 over root 5, plus mu is 1/4. R is 2 root 5 mg. And sine theta 1 over root 5 equals m omega squared. And actually small r, lowercase r, we have a number for this in terms of a. It was 1.5a, or 3 over 2a. So here I'm going to remind myself, 3 over 2a. Okay, this is good. We seem to know most things here apart from omega squared. So let's work with these and see what we can do. First step is I can get rid of m. Every term has an m, so let's cancel those out. Now let's deal with some fractions. We've got 2 root 5 multiplied by 2 over root 5. So actually here, the root 5 and the root 5 will cancel out. We have a similar thing in the next term with a root 5 on the numerator and denominator, so they also will cancel out. So here we're going to have 4g left over, 2g2. In our next term, we've got 1/4 times 2 times g times 1 that's left. So this should be plus 1/2 g. And then over on the right-hand side, we have 3 over 2a times omega squared. Almost there then where we need to be. So 4g plus 1/2 g, this should be 9 over 2g equals 3 over 2a omega squared. That might be the worst omega ever. We can multiply both sides by 2. So 9g equals 3a omega squared. Divide both sides by 3. 3g equals a omega squared. Get rid of our a, so 3g over a is omega squared. 3g over a equals omega squared. And last step, we can do a square root. So omega equals 3g over a square rooted radians per second. All done. Hope you enjoyed the video. I hope it was helpful to understanding circular motion in a cone. Thanks for watching.